Today we're looking at lesson 2.03, the name game. So today's objective is, we've actually got two. One is I can simplify an exponential expression in 1 out of 1 problem. And the other is I can match a sequence to its features in 1 out of 1 problem. So here are some things to think about. How do I know if a function is linear or exponential, regardless of what representation it's in? If it's an equation, if it's a table, if it's a graph, if it's a story. And then why are arithmetic sequences linear? Why are geometric sequences exponential? So the first thing we're going to look at is some exponential expressions. Remind me again what this means. What does 3 to the 4th represent to us? Well, remember this is 3 times 3 times 3 times 3. So we have 3 and we expand it out by multiplying it 4 times. So can we expand these out? 3 to the 4th times 3 squared. Well, sure. 3 to the 4th was just 3 4 times multiplied. And then we're multiplying in between them, and we're going to do 3 squared. So 3 2 times. 1, 2. Now if we count these up, we have 1, 2, 3, 4, 5, 6. So this is 3 to the 6th, which happens to be 3 to the 4 plus 2. So those are our original exponents. We can add them together. Similarly, let's look over here at dividing. So we have 4 to the 6th. That's 4 6 times. 1, 2, 3, 4, 5, 6 on the top of a fraction, and then 4 times on the bottom. 1, 2, 3, 4. Now we know with fractions that we can cancel the same number, right? We can cancel these 4s. So let's cancel these out in pairs. There's 1, there's 2, there's 3, there's 4, and we're left with 2 4s on top. So this is going to be 4 squared, right? That's our simplified expression. And this happens to be 4 to the 6 minus 4. So it will always work out that way, that the number on the bottom, the number of those factors on the bottom will cancel out with the ones on the top, and we can just subtract the exponents. So in general, we can write this like this. When you have the same base and you multiply an exponential expression, that means we can add the exponents together. Similarly, when we have the same base and we divide exponential expressions, we can subtract the exponents, the numerator exponent minus the denominator exponent. Now remember, you can memorize these. That's a totally fine thing to do if memorizing makes sense. These ones can be a little bit confusing for me to remember because I'm like, wait, I multiply and then I add, I divide, and that means I subtract. I don't always remember those. But do remember, you can always figure them out, right? You can just expand them out like we just did and then count them up, or expand them out and cancel them out. That is always an option if you can't remember these rules. So let's look at some examples here. Simplified to a single exponent. So we use this rule up here. When we multiply, we can add the exponents. This is going to be 2 to the 2 plus 5, which is 2 to the 7th. This will be 8 to the 3 plus 2, which is 8 to the 5th. Oh, this next one, we've got a variable as our base. Interesting. Does that change anything? Nah, that doesn't change anything. We can have a variable as a base. We just do the same rule. A to the 10 plus 7. That will be a to the 17th. And now we're going to use this other rule. When we divide, we subtract the exponents. So 9 to the 5 minus 2 will be 9 to the 3rd. This next one is 4 to the 12th minus 7, 12 minus 7 is 5, so 4 to the 5th. And we've got another variable here, b to the 8. So we'll do b to the 8 minus 4, which will be b to the 4th. Now what if we did something like 5 to the negative 5 times 5 to the 8? We haven't talked about negative exponents yet, or what they mean, but we could maybe guess that we can apply these same rules. We'll just get 5 to the negative 5 plus 8, which will be 5 to the 3rd. Negative 5 plus 8 is 3. So another law with exponents. If this is true, x squared equals x times x, right? That's just the definition of squared. That's the definition of our exponent here. Then what is this? 3 to the 4th, all of that squared. Well, it looks like 3 to the 4th is just our x value here, right? This is x squared, and this is x times x, so this will be 3 to the 4th times 3 to the 4th. And we just learned that we can add those exponents together when we're multiplying, so that's going to be 3 to the 8th. And you may notice this is the same as these two exponents multiplied together. 3 to the 4 times 2 is the same thing as 3 to the 8th. So once again, we can generalize this rule. If we have an exponential expression and we raise it to another power, then we multiply the exponents together. Once again, you can memorize this rule. There's nothing wrong with memorizing this rule, but you can also derive it. If you forget this rule, you're like, raising to a power means multiplying, maybe? You can always just write it out. Say this is squared, or this is to the 3rd, and we write it 3 times. You can always expand exponential expressions to figure out the laws. Here's a summary of the laws of exponents. This is a good slide to take a screenshot of, put in your notes. This just summarizes the 3 that we've gone over today. There are more laws of exponents than these. These aren't all of them, but these are the ones we're going over today. So let's look at a few more examples. We're going to look at some examples of that last rule we came up with, and then we're going to combine them. So 5 to the 6th raised to the 2, we decided that was going to be 5 to the 6 times 2 from this rule over here. This will be 5 to the 12th. The next one will be 6 to the 4th raised to the 3rd. We decided we multiply those exponents, so 6 to the 4 times 3 will be 6 to the 12th. This one we've got several steps, it looks like. Okay, so when we raise it to another exponent, we multiply. 4 to the 5 times 2. And then when we multiply, that means we add the exponent. That's the one up here. So now we're going to add a 3. This will be 4 to the 5 times 2 is 10, plus 3 equals 4 to the 13th overall. And our last one, once again, we've got a couple of steps we need to do. Here we multiply, there we'll subtract. So this is going to be 3 to the 2 times 7 minus 10. 2 times 7 is 14 minus 10 equals 3 to the 4th. All right, so that wraps up our simplifying exponential expressions. Now we are going to move on to a matching game. We're going to figure out functions in different representations. So first, let's match this equation over here on the left. We're going to match y equals negative 1/4 x plus 3. We're going to match it to one of these things over here on the side. Pause the video, Try to figure out which one you think matches, and then we'll go through them. All right, so let's look at A. This looks like a very gentle curve. And this is our mx plus b form. So this we know is a straight line. This is linear. Since this is a curve, we're probably going to think this is no. Another thing we can notice here is the y-intercept is 3. The y-intercept over here is 40. That does not match in any way. Okay, how about B? Continuous and exponential. Well, we just said this is linear, so it's not exponential. Can't be B. How about C? Oh, we've got a table. So I guess we could just take any of these numbers and plug them into the function and see if it works. So maybe I like 100. 100 is a nice number for easy multiplication. Let's try that one. So we'd have y equals negative 1/4 x plus 3. So negative 1/4, our x value is negative 100 times negative 100 plus 3. And we'd get y equals, this is going to be positive 25 because a negative times a negative is a positive. 1/4 times 100 is 25 plus 3. Y equals 28. So we were looking for these values. X is negative 100. We would expect it to be 44, but we got 28. 44 and 28 do not match. This is not the correct answer. So we've eliminated A, B, and C. The only option left is D. Let's see if it works. The domain is x is any real number. Is that true for a line? Can we plug any real number in here? Well, yeah, so like if we plugged in 0, that would work. If we plugged in 1, that would work. If we plugged in 100, we could resolve this. What if we plugged in a half? Sure, we can multiply fractions. That's not a problem. We could put in 0.00001. All of those would work. So D is our answer here. X is any real number. Next question. Actually, let's skip this one. Don't even worry about that one. Here's our next question. We're going to match this graph to one of these problems, one of these answers. Pause the video, try to figure out which one you think it is, and then we will go over them. Okay, so let's look at A. This looks very much like mx plus b, which we know is a straight line. Is this a straight line? It's not. That's a curve, so this is not the answer. B is continuous and linear. Well, we just said this isn't linear. This is a curve, so it's not that one. Then we have a table. We can look at each of these points and see if they match the graph. So let's see, negative 1.5, 0.3535. So negative 1.5 is going to be here, negative 1.5. And our point's going to be right about there, which is about 0.3535. That's about a third of the way up to 1. How about 0, 1? Is 0, 1 on this graph? 0, 1 is right here. Yeah, that looks right. How about 0.5, 1.414? So 0.5 is going to be right here. And that is about 1.4, yeah. So here's 1, and it's little, almost halfway up. So these points all look like they fit. C seems like it might be a good option. Let's eliminate D. So why would this not be correct? X is greater than 0. Well, it's because if you look over here, X values below 0 also work. All of this down here is a valid function. It's part of our function. So our domain is not just X is greater than 0. It's also X is less than or equal to 0. It's X is all real numbers. So this is not correct because X can be other numbers than just the ones greater than 0. C is our answer here. Next problem. Match this equation to one of these representations. Pause the video, see if you can figure it out. So let's look here. This is mx plus b format. It's kind of a complicated complicated slope, but that's okay. We can have complicated slopes. We can have fractions. We can have negative numbers. We do know that the y-intercept here should be 40, which looks right. That looks like it's where it crosses the y-axis. This is a negative slope, and this is going down, so that matches. We could even calculate out the slope, although that looks pretty nasty and I don't want to do it right now. So maybe let's leave A open as an option, and let's see if we can eliminate any of the other ones. How about discrete and linear? Well, this is the equation of a line, so this is linear. What about discrete? Would we expect this to be discrete? Well, if we have a line, anywhere we draw a line, we could draw one there, we could draw it here, we could draw it like that. Any of those lines, are those continuous or do they have jumping points? Lines are continuous unless they tell us otherwise, something about the domain is restricted. So since they didn't tell us anything is restricted here, we'd have to assume this line is continuous. So discrete is not our answer, and this one is not correct. How about this one, this table? One thing you might be able to identify right away is this y-intercept. Our value at 0 should be negative 15. We don't even have a negative 15 on the graph. That'd be way down here. So this doesn't seem to be the case. And then on D, it says our domain is x is a whole number. Oh, but look, this looks, we already said this is continuous, right? So if it were discrete, we'd expect it to be whole numbers. Whole numbers would be discrete. But like we said, we expect this to be a continuous line. So D is not our answer here because this should be a continuous line, and whole numbers are not continuous. A is our only option left. We're going to go with it. It seemed to match. Seems like a good option for this one. Here is our last problem. Pause the video. Decide which of these options goes with this graph. Okay, so we have, this looks like a curve, and it's jumping. We don't have a continuous line here. So let's look at our options. F of n equals 0.25 times 2 to the n. Okay, so this is, we recognize this form as a times b to the x. That's an exponential. We would expect that to be a curve, and it is a curve, so that matches. They've also told us that n, the domain is n, is a whole number. Let's see, this 0 is a whole number, 1's a whole number, 2. Okay, so that seems to match so far. We'll leave that one open, see if it works. B is discrete and linear. Well, it is discrete. These are jumping from point to point. How about linear? Is that a straight line? No, this is a curve, so that doesn't work. Here we have our table. 0, negative 15, our value at 0. Is that negative 15? Okay, once again, this would be way off the graph down here. So that point isn't there. This one is not our option. And D says the domain is x is any real number. Well, what about 1/2? 1/2 is a real number. Is there a point at 1/2? Or at 3/2 right here? Is there a point there? This function doesn't seem to exist in between the whole numbers. So this is not the correct domain. The domain should be whole numbers. Once again, the only one we have left is A, and it does seem to fit. It is a curve, it is exponential, It has the right y-intercept because of that 0.25 right there. It's our value at 0. And n is a whole number. The domain matches. So all of those things match. We're going to go with A on this one. So that covers today's objectives. I can simplify an exponential expression in 1 out of 1 problem, and also I can match a sequence to its features in 1 out of 1 problem.